Okay, let's talk about current, electricity and electrical circuits. So you've already done electrical circuits in grade 8 and 9, and also there's a certain amount of it in technology. So in order to have an electric current flowing in an electric circuit, you have to have a source of energy. So we often, until grade 12, we're just going to look at a battery as our source of energy, okay? And the battery provides the energy to do work. You need conductors, because how do you get the energy from the source of energy to wherever you want it to do work? And then finally a closed circuit. You can see these two pictures are identical, and the little red dots are electrons, which are the flow of current. And when the circuit is open, the electrons can go nowhere. Okay, I like to say the electrons come out the battery and then they try to go home again through the circuit. But if you check and you're an electron that you come out the battery here, you can't go home through an open circuit. But if you look over here, all of these little electrons are traveling through the closed circuit. When they reach the light bulb, they do some work and they drop off their energy, and then they come home to the battery, because electrons always leave the battery and want to come home to the battery. Or at least that's how I like to picture it, because it helps me work my way through electricity problems. It's not like electrons really have desires and dreams, but they do need to complete the circuit. So this diagram here is my favorite picture of electricity, and when I think of electricity, this is what I think. The volt is the potential difference, and this is pushing the current through the circuit. So the current is this fellow amp. So Mr. Volt provides the push to the circuit. He's the potential difference. He pushes the current, the flow of electrons, through the circuit. And Mr. Ohm, who is very cool in his cowboy hat, is the resistor. And the resistor kind of like squeezes the current. He makes it hard for the current to flow through the circuit. So whenever I think of these electricity problems, I think of the volt pushing the current and the resistance squeezing the current, making it hard for the current to get to where it wants to go. So we've always talked about voltage. We now are nearly always going to refer to voltage as potential difference. But when you read potential difference, you have to think about volts, and we measure the potential difference in volts. Current is measured in amps, and resistance is measured in ohms, which is this Greek letter omega. I always call current amps, but its proper name is amperes. So this is a capital V unit, this is a capital A, and this is this omega ohms. How actually does electricity work? If you've got a conductor that is a metal, like for instance copper wire, you've learned in chemistry that you have positive atomic cores, where you've got the protons and the core electron shells. And in a metal, in metallic bonding, the valence electrons are free to move between the different atoms. So here you have a conductor sitting at rest, but it's just sitting there, but meanwhile all the electrons are small and whizzy, and they are just randomly moving around in amongst the atoms. And this is going on and we can't detect it, but electrons are small and whizzy, and the whole time they're just running around between all of the atoms. We now then make a potential difference with this battery. This battery is like a little electron pump, okay? And the battery provides a potential difference. And now all the electrons get organized and they flow from atom to atom in a particular direction until they return to the battery and complete the circuit. So electrons travel in a circuit via the potential difference. They move from an area of high potential to an area of low potential. And the whole reason why metals can conduct electricity is because they have these loose valence electrons that can be popped from one atom to another atom. So then we come to the mechanics of this subject. It all relies on understanding circuit diagrams. So if you ever get asked to draw a circuit diagram, which is not actually very common, you must have it with a sharp pencil. You need a ruler. You don't have to put ammeter A and then draw a little arrow and write ammeter, resistor. We all use standard symbols, and because we use standard symbols, everybody knows this A is an ammeter, this little box is a resistor. There are two batteries over here. the circuit is not closed. Here's the open switch, okay? So you can move certain things around so long as what's in parallel is in parallel, what's in series is in series. So this ammeter could be here, it could be here, it could be here. It makes no difference in the context of this circuit. So you just have to realize what all the components are. These are the components you need to know. A straight line for a conductor, a little box for a resistor. Sometimes in old diagrams they draw that zigzag line for a resistor as well. Here's a light bulb, the circle with a cross, a cell, a long pole, and a short pole. The long pole is the positive pole, and this is the negative pole. This open switch we know, a closed switch. Here the two dots indicate that there's a switch in this conductor. Voltmeters always connected in parallel. Can you see here if you are in parallel, if the current is coming this way, it has a choice at this point. Does it go this way or does it pass through the voltmeter? Voltmeters in parallel. Ammeters in series, it just goes shoop, straight through the ammeter. The current's got no choice where it can go to. And this one here is one that I don't think you've used much before, so you need to learn to recognize this. This is a rheostat or a variable resistor. It gets called either of them, and it's a resistor with an arrow, which is kind of like showing you that it's a gauge that can flick from left to right. So the rheostat is the ordinary resistor symbol with an arrow through it. So let's talk about the two different kinds of circuits we have. We have a series circuit and a parallel circuit. In a series circuit, there's only one path for the current to flow, okay? The current can go nowhere else. It can only go on this one route. And what is important about a series circuit that you always have to remember, this is like the key to understanding circuit diagrams when they give you a current in one place and they expect you to find it in another place. In a series circuit, the current strength is the same everywhere. The amps are equal, okay? However, in a series circuit, the potential difference or the voltage, whenever you see potential difference, sometimes in your mind you can go potential difference is voltage. We use the term potential difference because it's more accurate, but you're going to measure it in volts. So just like I said, the current strength is the same at all points. The amps are the same at all points. If the potential difference is divided, the volts are divided, okay? So how does the potential difference divide up? It's not just random. The potential difference divides across the resistors in the same ratio as the resistance. So if you've got an 8 ohm resistor and a 4 ohm resistor, the 8 ohm resistor's got more potential difference and the 4 ohms got less potential difference, and the voltage will be in the same ratio as the ohms. And also in a series circuit, this is the way we would say this same ratio, the voltage is proportional to the resistance. Remember V for voltage or V for potential difference, and then this symbol here is the directly proportional to symbol. It means they have a directly proportional relationship. If V gets bigger, R gets bigger. If V gets bigger, R gets bigger. If V gets smaller, R gets smaller. That is a directly proportional relationship. So the greater the resistance, the greater the potential difference for the same current through the resistors. These two are the same things, just expressed slightly differently. What happens in a parallel circuit? In a parallel circuit, the current has what I call choices. Obviously, it's not choosing, but I like to use these words to help you think about it. There's more than one path for the current to flow, so when the current reaches a junction, it can choose which path it's going to flow down. Now, this is the key to understanding parallel circuits. The potential difference across the parallel components is the same. So you see this sentence here in red in the series circuit, and this sentence here in blue in the parallel circuit. These are the keys to working out what's going on in your circuit diagram. If you've got a bunch of parallel resistors, they will all have the same potential difference. But the current is lazy, okay? The current divides, and it does divide according to the resistance of each resistor. But if you look here, it says the current is inversely proportional to the resistance in a parallel circuit. So I always call this current takes the easiest path, okay? So it says here, the resistor with the greatest resistance will have the smallest current flowing through it if the resistors have the same potential difference, okay? So this thing says to you, in a parallel circuit, the potential difference is the same everywhere. So if I've got 3 parallel resistors, and one of them is 2 ohms, one of them is 6 ohms, and one of them is 12 ohms, the current will take the easiest path, and nearly all of the current will go through the 2 ohm resistor, and very little current will go through the 12 ohm resistor, because that's just how current works in a parallel circuit. If the current is given a choice, most of the current will go through the easiest path being the smallest resistance. So an inversely proportional relationship means big current, small resistance, okay? So small current, big resistance. That's what an inversely proportional relationship means. If we look at a charge, so the charge is basically an electron, a charge plus or minus, it's electrons, so they're minus. So if you put a charge in an electrical field, okay, we usually think of electrical fields with static electricity. So if you think of something that's charged with static, it's actually got energy because it can zap you, okay? So if we put a charge, for instance an electron, in an electrical field, it can do work. It has potential energy. If you have energy, you can do work, okay? So unless something's stopping you, this charge, the electron basically, will move unless there's something in its way, okay? So have a look at this. Look at this diagram. If you've got a ball, this ball can do work if you lift it above the surface of the earth. If you lift it like 1 meter above the surface of the earth and you drop it, for instance, on your foot, okay, your foot is not going to get very damaged because 1 meter, it's not far, and the earth's gravitational field has not given it that much energy at 1 meter in height. But if I take this ball and I move it, say, to the top of some tall building, not one in Hoedspruit, some very tall building, okay, say a 10-meter high building, and I drop this ball. When the ball is at the top of the 10-meter building, it has a lot more potential energy. As it falls and lands on my foot, it's going to do a lot more work on my foot, and I'll probably end up at the doctor, okay? So charges are exactly like this. You have to think of this electric field, okay, as just existing like gravity exists, electrical fields exist, and if you put a charged particle in that field, it's going to work. It's going to do work. It will move and do work. And depending on where you are in your field, depends on how much work you're going to do. So we then have a potential difference. Can you see here has potential difference A and here has potential difference B, depending on where you are in relation to your electrical field. So a potential difference is a difference in potential energy between 2 points. And potential difference, the moment there's a potential difference, the charge is going to move, and the moment the charge moves, it can do work. So the charge will always, the charge, the electron, the minus, the charge will always move from high potential energy to low potential energy. And this is what we use to do work. And the kind of work can be, for instance, light energy through a light bulb, heat energy from your heater or your electric blanket, or it can be noise from your radio, things like that. And remember what we said to you about resistance and potential difference. As the resistance increases, the potential difference increases. One of the ways they encourage people to think about this is like water in a hose pipe. Say you've got a water pump or your tap and the water's under pressure in your tap, okay? If you pump that water out and you put it through a resistance, okay, the pressure will change here and it'll come back at low pressure, okay? The same with current. If there's a high potential at the one end of your battery, it pushes the current out. As it goes through the resistance, it comes back with a lower potential energy. So this hose pipe theory works. If you think of a big fat hose pipe and then you squash it down to a tiny skinny little hose pipe, then the water pressure changes through the hose pipe. And this is the same with current. These little electrons or charges come out of the power supply. They are ramped up with their energy. They've got so much energy. They run through the resistor. They offload some of their energy, and then they come back at a low potential energy back to the power supply. So this is the job of a battery. It's like a little electron pump, but we always say a battery converts chemical energy to electrical energy. Remember, energy can neither be created nor destroyed. It can only be converted from one form of energy to another. So the battery converts chemical energy into electrical energy. So inside your battery, you've got anions and cations, and when you complete the circuit, they're allowed to move between the positive and negative terminals, and this allows them to flow in the external circuit as well, because this is acting kind of like a little electron pump. Okay, so the anions and the cations move between the positive and negative electrodes, and then the electrons complete the circuit externally. So in a battery, the battery uses chemical energy and converts it to electrical energy, but there are chemicals in here. So why does your battery go flat? Your battery goes flat because the chemical reaction is finished. All of your anions and cations in here have undergone a chemical reaction until they've gone from reactants to products, and there are no more reactants to push the electrons in the external circuit. Because the moment you put the battery in the circuit and you put the light bulb, your toy, whatever in the external circuit, as the electrons move through here, the energy that they left the battery with, it's transformed now. The chemical energy goes to electrical energy, which goes to light and heat and noise and whatever, and then the little low potential electrons go back and the chemical energy is used up. And here I'm going to stop for now.